Well, good afternoon, ladies and gentlemen. My name's Andrew Starr. I'm going to present to you this afternoon on keeping the wheels turning, maintenance research, past, present and future, which is going to be a light-hearted and in places serious view on the world of maintenance. Firstly, I'm going to examine the nature of maintenance, what it is and what people believe it to be, but more formally some of the ways in which people have defined it. I'm going to take a nostalgic view to some extent through ancient times and through the development of where maintenance has got to today, before looking at some of the more recent rapid progress, the important steps. I'm only going to dwell lightly on the state of the art because the people in this room are such experts in it that it would take me the rest of the evening to go through all their expertise. However, I'm going to try and gaze into the crystal ball of the future and to see some of the problems that are on the horizon. I lead a centre which tries to form partnerships with industry and with academia to look at solutions for operations, for assets, right through the breadth of design, management and system sustainment. And we have today a term, through life engineering services, which provides the support throughout that period. The formal definition of maintenance is simply this: a set of organised activities carried out in order to keep an item in its best operational condition. Of course, with this important rider with minimal overall cost. But in many people's mind, maintenance is about the fellow on the right who is doing a repair. Of course, in practice, maintenance is divided up into a whole range of different tasks of planned and unplanned maintenance, and this diagram will be familiar to many specialists in the audience. And under the planned area, those areas of preventive, predictive improvements and corrective maintenance are part of our bread and butter. But quite importantly, that doesn't underline why maintenance is important. Things break, and we want to try to prevent failure from occurring, and very importantly, we want to try and minimise the consequences of failure. The images to the right are of a helicopter which failed in the North Sea in 2009, and it went down with 16 lives in broad daylight. This helicopter had been passed for flight by human operators after an incident on its monitoring system, and in fact it was caused by a fatigue failure through a gear in its final drive. So whatever we think we've done over the last few hundred years of maintenance practice and improvement, we haven't solved all the problems yet. We can extend the requirements of that simple definition of maintenance by thinking about the avoidance of failure in so-called critical situations. And those are in three key areas. High capital costs, where we have high-value assets, which could become damaged. Safety and the environment. And the environment's been added to this in the sense of sustainability in only the last few years, considering the impact on pollution and the use of excess energy and carbon dioxide release. And of course, one of the key areas of the interruption to high-value production, when we consider the rate at which we produce power and consumer goods and consumable products like paper, for example. One of the key combinations that we need within the maintenance process is to put together both a clear management strategy and practice, but also technical solutions so that we can improve that practice. And today we also want to underline that maintenance is not a separate activity, but a combined activity that adds value to a business for the long term. Quite importantly, we also work hard to put together standards and the requisite training to make sure that the people associated with such practices are contributors as well. Let's think about maintenance in ancient times. There are three key areas that we might divide it into. The domestic maintenance of house and home, industrial maintenance, and of course military activity. Some authors have recorded that domestic maintenance is badly recorded because it was women's work. However, I think we can be pretty clear that both men and women were in the daily activity of repairing houses and ensuring that food was prepared. And this was the question of existence. But as we get beyond that and we think about the way in which ancient industry started to create its own infrastructure and started to use milling processes and mechanical processes using, for example, animal power and water power to produce chemicals, metals and wood-based products, then there's a great deal more activity took place. And also, if we look at some of the military engines, as we'll look at in a moment, then you'll see that some of the mechanisms there were absolutely critical. But there remains very little written record of the type of maintenance that took place for these. Let's take an example of milling. The use of stones for milling goes back thousands of years. And the development of flat stones into rollers and then the pivoting of those rollers to make them take an action and the associated friction of them has always been a problem which early millers needed to cope with. They're used for a whole range of different processes, and the modern day milling process is not fundamentally different. But even in ancient times, this gave rise to a couple of phenomena that have been absolutely crucial ever since, and that's the pivot and associated friction processes. The gears and bearings associated with turning stones go back to Roman, potentially Greek times, and wood has always been a good material for cutting complicated processes, and you can see how the right shape of gear teeth can give us continuous motion and change both the torque, the moment, and also speeds. However, to turn things around a pivot requires one round bit of wood or metal to turn in a wooden socket, and of course this is a recipe for friction, and of course it's quite a good way to light a fire, which is one of the reasons that we don't have ancient mills generally in existence. The people who built such mills, the millwrights, were able to make such machines from basic materials. And they also repaired and kept working such machines for hundreds of years. The types of human senses that they used to help monitor such processes are not recorded, but they must have used their ears, their eyes, and their noses to be able to determine the state of health of the machines around them. Now, of course, in the sense of research, we don't have the recorded observations of those people, but we're certainly building on their foundations. Our colleagues in the defence world developed a whole range of military devices, and their problem has always been that they had plenty of time to build them and plenty of time to haul them to places, but then they were used intensively, and in between they had periods of inactivity where they might be able to repair such a machine. But the reliability of being able to get essentially a guided weapon from the place that you launch it to its target has always been the prerequisite. To be able to repair such a device and to be able to make it effective has always been important for this type of machine. So it's made of basic materials, of basic designs. It's also important to note that the first engineers were all military engineers, and the term civil engineer is the term for any engineer who's not a military engineer. So that leads me on to think about why we need maintenance in the sense of things that don't last forever. Why do things fail? How do they degrade? In the next few slides, I'm going to talk about things that last an awful long time, long life assets. And that really is the things that we aim at in design in good practice. But all of the phenomena of friction, fatigue, chemical aging, the using up of properties, and loading exceeding the design strength are areas where we really bring down the life of our assets. As a first example, the Menai suspension bridge was built in the years approaching 1826 by Telford as part of his scheme to connect Anglesey with London via the A5 road, which was developed all through southern England and Wales as a new venture to straighten it, to reduce its gradients. And at that point, the Menai Straits could only be crossed by water on a boat. This was the first long chain suspension bridge in the world. It was the longest span in the world. And you can see from the timeline that the maintenance for this bridge started almost immediately. The reason that happened was that in those days the quality control on both the materials and the assembly was a challenge, and the ability to measure some of the distribution of loads was also a challenge. So we see that as time goes on, this long-lived structure, which is in daily use today, has had a series of repairs and, in many cases, preventive actions to increase its capacity and to prevent catastrophic failure, which, of course, has occurred on some bridges. During this Victorian period, we also see a very great rise in the use of bearings, particularly in the rise of the railways. And early bearings were all a form of journal bearing. That's a plain cylindrical bearing, and the lubrication was absolutely essential for this type of bearing. In former times, the lubricants were derived from vegetable or animal fats, and their chemical degradation was in fact quite rapid. So as a consequence, the maintenance of the lubricant was essential to be able to keep the bearing turning properly. And of course, if the lubrication is taken away from such a bearing, the amount of friction increases rapidly, and then the temperature increases and the iron degrades very rapidly, and friction occurs. Another important process led to this disaster in Versailles in 1842, where fatigue occurred in a railway axle shaft and caused a catastrophic failure in the locomotive. And this is, of course, an artist's impression. It predates photography. However, what happened was that the train collapsed into the back of the engine, and the dropped fire from the engine caused the leading carriages to catch fire, and of course that caused a lot of injury and indeed death. So following on from accidents of this sort, a great deal of research was taken place to identify the sources and the progress of cracking. And again, there's a timeline associated with this that runs through the 19th and 20th centuries to identify the nature of this particular problem. Now, of course, this may look like ancient history, but fatigue is always with us. And we have all kinds of processes in place to try to avoid it, but there are still catastrophic accidents that occur because of fatigue. You also see some key words in this timeline, for example, of the stress concentration, which starts to initiate the crack, and of the cyclic stress that causes the propagation of the crack. And really those processes, whilst they are analysed in certain situations, are still not fully understood in some of our new applications. The nature of the bearing problem led to innovation, which almost took the problem away in the form of rolling element bearings. Rolling element bearings again go back to ancient times. When you consider, for example, rollers being used under pieces of stone to move them more freely, then it's clear that ancient engineers used these. However, the cage as part of a roller bearing or ball bearing didn't appear until around 1750, when Harrison, who was engaged in the longitude problem, started to use them in his H2 clock. H2 was never used, but nonetheless you can see it at Greenwich to this day with its first roller bearing, with its balls made out of lignum vitae wood. The big change probably came in the early 20th century, and Conrad's patent is for the deep groove ball bearing, where essentially the inner and outer race have no holes in, they're continuous, and the balls are inserted into the lower part of the race and essentially half fill the race so that the inner race can be popped in between and the balls can be separated by a cage.